Alright, welcome everybody. This is a Team Adams presentation on Chapter 8, Observing Facts and Tracking Origins. And we have our little sponsor down there in the right hand corner of our team logo. So our team is made up of 3 members, Eric, Zach, and Desiree, and we will all be alternating presenting during this presentation. So to start out, there's really 3 main principles of observation you want to keep in mind during your debugging process. First one is do not interfere. So you pretty much just want to observe the original run for how it is. You don't want to think you observed something that wasn't there. You don't really want to change anything you don't need to be changing. You just want to observe it as it usually would run, and you want to observe it all the way through to the end so you can see the causes and effects of the issue. The second one is know what and when to observe. So programs can be huge, and it's very important to know what variables, what code you need to be looking at in order to optimize your time debugging. Otherwise, you'll just be wasting your time looking at stuff you don't really need to, and nobody likes doing that. And lastly, you want to proceed systematically and use a scientific method. Just like with everything else we do, pretty much you want to use a scientific method to come up with a hypothesis and test it and redo it if you need to. So the first debugging method we're going to get into is called logging. It's probably the most simplest and straightforward method to debug. I'm sure we're all familiar with what it is. We've all used it at least once in our coding career so far. It's where you insert logging statements into the code to check the flow, check variables, whatever you need it to do. Make sure that it's not unreachable code too. It goes by many other names: printf debugging, printline debugging, console log debugging. It really depends on the language you're using and what it would be called. And one of the main benefits of logging is that it's always available in some form, whether you're doing software or hardware. Software with the console logs and hardware through LEDs. So no matter what, you can always use it, which is a really good thing. It's a nice, quick, dirty way to get some debugging in. And on the right hand side you can see an example of some printfs inside my switch statement, which will debug which case is going to be picked when that code is executed. So logging is good because it is always available no matter what software language you're using or hardware really. But that ease of access definitely comes with some problems. It's not perfect. It can clutter your code and clutter your output, especially your output if your program's already outputting data already. And if you use the same output stream for debugging, you're definitely going to get some clutter there, and it's going to be hard to see what's actually being outputted by the program and what's being outputted by your debug lines. Another problem is that it can slow down your code. Anything that you put in your source code is going to slow it down a little bit through the compilation time and the execution time. But it's nothing too serious, but it is something to keep in mind, and it can add up if you have large amounts of these logging statements in your program. And another issue is you can have a loss of data. So usually before a program outputs the log statement to the console, it puts it in a buffer first, and this log can be lost if the program crashes or segfaults while the log statement is still inside the buffer. So a way to combat this is to create an exception or some way of your program to flush the buffer out before it fully crashes. That way you can still see your logging statement that was in there. So some of the ways you can combat some of the problems with logging is by using logging standards. Some of the standards you can incorporate are using standard formats, so include the word log or something else maybe in the beginning or at the end of your logging statement. That way it's easier to identify that it's coming from your log and not your program output. You can make logging optional. It will increase your performance, usually done in production code via the compiler. Allow for variable granularity, so only focus on the level of detail that you need. Don't focus on stuff you don't need. Stay within the scope of your problem that you're debugging. Also, you can be persistent. So if you are going to keep the log statements in your code, it's important to be persistent about it. That way you can reuse them in case the same problem occurs or a similar problem occurs. Also, a good standard to do is have specific macros, which we'll look at here in a little bit, and they really does help with maintaining logging statements and enabling them and denabling them. So now we're going to go over logging functions and logging macros. A logging function is a specific function designed for logging purposes only, and it's probably one of the most easiest ways to customize your logging statements because you can just call it from where you want it to be executed, and the function will run from there. The logging macro is code that expands to a logging statement or a no-op, and just examples of the logging macro on the right-hand side. The top example is kind of a skeleton, and then the bottom example is an implementation of the skeleton. So depending on if the debug variable is true or false, 1 or 0, it will get expanded into the cout, or it will be expanded into a no-op. It won't do anything at all, and really comes down to the compiler settings and how if you have the program in debug mode or not, will determine the outcome of that. And using logging macros is really only beneficial in languages with preprocessors where the compiler can make the choice to expand it or not expand it. So one of the frameworks you can use to help implement some logging standards and logging in general is the Log4j. Log4Java, created by Apache, and is an open source Java-based logging utility tool. It's really good because it provides a way to customize almost every aspect of logging. And we have an example of it on the right here from the textbook. You can see the logger being created and assigned to the test logging class. And then right underneath that, in the static void main function, the logger.bug, debug logger.info, logger.warn are all extensions and different levels of logs which you can choose to output, which is really nice. Another good function of this is it also provides appenders, so you can direct the log to a specific output, ideally different than your program output. That way you can keep them separated. So the log4j, you do keep the logging statements still in your source code. However, you do have the option to really customize your level of logging and which classes you do give the logger to and where you could set the output to, which is really nice and beneficial. And it's all like all-in-one package there. It is also available in different versions in C, C++, C#, Perl, Python, Ruby, and Eiffel. However, I think it's mainly used in Java though. So another good thing about the Log4j framework is it comes with a analyst tool called Chainsaw, which is a graphic user interface for analyzing your log files or logging statements. Here is a example picture of what it looks like. As you can see, these are all the logs that were displayed during the program's execution. And as you can see, it displays the different levels of logs, the info, warn, error, and color codes each one real nice so it's easy to see. It also displays the logger so you can see where in the code it came from, and it also gives you a little message so you can kind of get an idea what went wrong there before you go and look at the issue. So up to this point we've discussed logging where you include the logging statements inside your source code. However, there is a way you can do it also where you keep the logging statements and your source code in what we call two different aspects. And the logging aspect is what we're going to get into here, and you can see an example of it on the right, the log by aspect. So yeah, these aspects are nice because they're separate from your source code. They're not going to get cluttered or anything like that. It is in its own little file. And inside these aspects are things we call advice, which is the actual code that's going to get executed. So the sysout print line is the advice in this specific aspect. And the locations in which the aspects are called, it's called a point cut. So we have a point cut here called by method, and it's called every time the by method from the article class is executed. Before and after those lines will be printed. And point cuts consist of joint points, which is a point in the program where the advice is actually applied. So a point cut is made up of a set of joint points.
Debuggers provide three functionalities to help you observe actual execution. execute the program and make it stop on specified conditions, observe the state of the stop program, and change the state of the stop program. An example of a debugger in the GNU debugger is the GDB. It's an interactive program controlled via a command line. Debugging with GDB. In here we have a sample program that's supposed to sort its arguments. However, when invoked with 11 and 14, the output is 0 and 11. We must first prepare the program for debugging. This means to have the compiler include debugging information in the generated executable. Debuggers need this information to know where a particular item is stored. Next, we load the program in the debugger, and then you're in the GDB command line. We must first decide where to stop the program such that its state can be examined. In here, we set a breakpoint that will make sample's execution stop at line 38. Now we can run the program with the failure-inducing arguments. In here, we have other functions that the GDB provide. You have print, step, next, set, continue, and frame. Embedded debuggers. One might also set up a system such that it invokes a debugger on itself. The following piece of code invokes the interpreter in the middle of a loop by invoking the Python code.interact function. Breakpoints. GDB provides a feature called data breakpoints or watch points to catch a specific moment in which a given condition comes true. In some cases, one might also be interested in having a program stop on a specific condition and the specific location in which the breakpoint comes in handy. It's a breakpoint that stops only under certain conditions. Coca Debugger, a front end to GDB that provides a uniform query for arbitrary events during execution. In Coca, event and data are characterized by attributes used in queries to obtain all events or data where the query will be satisfied. Queries typically consist of two parts: queries that denote the subset of the execution time in which the given attributes hold. By time, using attributes denotes all events in which the current function will be the shell sort for that function equals shell sort. And space, which uses current data attributes. For example, a query with current data type int denotes all data of which type is int. In here we have different tools that can be used for debugging: Log4j, AspectJ, GDB, DDD, or EDOBS. Omniscient debugging is to explore the execution history backwards. We record the execution, every single change to every single aspect of the line. This idea has been realized under the name of omniscient debugging. Using ODB, one can step back and forth between timestamps specific to the individual windows. The programmer can also issue event queries and directly jump to specific events. Pros for it are random access to every moment in time and every aspect of the execution without needing to restart the program. But the cons is that recording all the state changes is expensive. Recording will typically slow the program down. In addition, it requires a lot of memory.
Dynamic slicing. A dynamic program slice is an executable part of the original program that preserves part of the program's behavior for a specific input with respect to a subset of selected variables, rather than for all possible computations. As a result, the size of a slice can be significantly reduced. Dynamic slicing is used for finding the dependencies for a concrete run in order to trace back origins, which allows us to find where the bug occurred. Static versus dynamic slicing. As you can see for example A, the static backward slice of S being outputted in line 15 encompasses the entire program, while in example B, the dynamic slice applies to the run in which n is equal to 2 and a is equal to 0. This is an example of the code we're about to go over. On the left, all of the traces are labeled for us. Dynamic slice steps. For each write w to a variable, assign an empty dynamic slice. Proceed forward through the trace, or execute the program generating the trace. Whenever a value w is written, consider all variables r read in that statement. For each r, consider the line r where r was last written, as well as its dynamic slice, dyn slice r. Compute the union of these lines and slices and assign it to the right of w. At the end of the execution, all definitions will be assigned a slice that holds all origins of all values. And you'll see what that means in a little bit. For this example, consider the dynamic slice of line 4, dyn slice 4. In line 4, b is written while a and x are read. A and x were last written in lines 2 and 3. Therefore, the dynamic slice of b in line 4 is the union of the dynamic slice of a in line 2, which is empty, the dynamic slice of x in line 3, which is also empty, and lines 2 and 3. And you can see on the bottom the formal definition. Not everything with dynamic slicing is great. On average, dynamic slices are far more precise and smaller than static slices, which is good. In a concrete run, all locations of all variables are known, eliminating conservative approximation. Likewise, in a concrete run, paths that were not taken need not be taken into account. A static backward slice usually has 30% of a program's statements, while a dynamic slice only has about 5%. Here's where it gets bad. They have two main downfalls to dynamic slicing. One is overhead. Dynamic slices depend on a trace of the program, which is difficult to obtain efficiently. Although we need not record the entire value history, as in omniscient debugging, we still need to record which statements were taken in which order. 2, lack of generality. Dynamic slices only apply to a single run of the program, and thus cannot be reused for other runs, in contrast to program dependence graphs and static slices, which are valid for all runs. Y-line debugger. Y-line stands for workplace that helps you link instructions to numbers and events. It is a debugger whereby programmers can ask questions about why things happened and why other things did not happen. It's a program where you can ask, why did my program fail? It was originally designed for Alice. On the bottom is an example of a program called Pac-Man. The protagonist, Pac, has collided with the ghost, but does not shrink as it should. It should resize to 0.5. If you ask the debugger, hey, why did this break? Why did this not work? The answer to the previous code is shown below. The diagnosis comes as a chain of dependencies ending at the else branch, consisting of the following events. 1. The big dot that is eaten is set to true. 2. Therefore, the is eaten variable is true. 3. The negotiation not from the previous code is false. 4. Although Pac is within 2 meters of ghost is true. 5. The and conjunction from the previous code evaluates to false. 6. Therefore, the else clause is taken. And this is showing you all the steps it took to get to the result that says, hey, this did something else that you didn't want it to do, and these are the reasons why. Tracking infections. The following is a general strategy that combines observation and dependencies to narrow down arbitrary infection sites, a strategy for locating arbitrary defects. Start with the infected value as reported by the failure. Follow back the dependencies to potential origins. This can be done using static or dynamic dependencies. Observe the origins and judge whether the individual origins are infected or not. If found early infected value, repeat steps 2 and 3 to track its origins. When you find the infected value v, where all the values that v depend on are same, you have found the infected site, the defect. Fix the defect and verify the failure no longer occurs. What's missing from this is just watching the code run. If you find a bug, just see where it goes, because it could find other bugs in your program. One of the tools we went over was the ODB debugger, and it was developed by Lewis in 2003, who also coined the term omniscient debugging.